Welcome to Lesson 19, Series and Parallel Circuit Rules. Today we learn how circuits share things out. Here's the plan for today. Let's start with the most fundamental rule. Current is conserved at a junction. Charge can't pile up at a corner, and it can't materialise out of nowhere. So whatever flows in must flow out. Two wires each carrying 1 amp meeting at a junction gives you 2 amps flowing on. In a series circuit, there's only one path, so the current is the same everywhere. And here's the misconception. The current is not used up as it goes round. The electrons aren't consumed. They give their energy, but they all keep going. Same current before and after the lamp. In parallel, however, the current has a choice of routes, so it splits between the branches, like cars spreading across the lanes of a motorway, and then merges back together afterwards. So the total current equals the sum of the branch currents. Now voltage. And I want you to picture each electron setting off from the cell carrying a few packets of energy. As it passes through each component, that component takes 1 or 2 of the packets. By the time it gets back to the cell, the energy is empty, and the cell tops it back up, ready to go round again. In series, the components each take their energy in turn, so the individual potential differences add up to the supply voltage. You step down from the supply height to 0 as you go around. In parallel, however, each branch runs from the same point to the same point, so whichever route an electron takes, it drops through the same potential difference. Every parallel branch gets the full potential difference across it. Now let's derive the resistance rules, rather than just memorising them. It makes the understanding far more secure. In both cases, we use Ohm's law, such that the total voltage equals the total current times the total resistance. For series, we have V1 equals I1 R1, etc. In series, the total voltage drop equals the sum of the voltage drops across each resistor, so V total equals V1 plus V2 plus V3. This means that I total times R total equals I1 R1 plus I2 R2 plus I3 R3. But in series, we said that the current is all the same, so we can factor out the current and divide through to get rid of it. This means that the total resistance is R1 plus R2 plus R3, and in general, the total resistance in series is the sum of each individual resistance. In parallel, it's the other way round. Now the potential difference V is the same across both resistors, and it's the currents that add. We rearrange Ohm's law to get the current total equals the total voltage over the total resistance. Now in parallel, we add the currents, so the total current equals I1 plus I2 plus I3. Substituting Ohm's law gives the total voltage over the total resistance equals V1 over R1 plus V2 over R2 plus V3 over R3. In parallel, the voltage is the same across all branches, so we can factor that out, and we get the relationship that 1 over the total resistance is the sum of 1 over all of the other resistances. Make sure you're careful with this, as you need to usually plug the numbers in first before you calculate the final resistance. That's the end of the video. Thanks so much for watching. Check out my tutoring page below.